equation of the process was 1, then the shocks only would have permanent effects. So it seemed on the basis of the univariate models, well, either you have temporary effects or you have permanent effects, but not a combination of the two. And that is something that we asked will allow us to bring in that we have some shocks that have permanent effects and other shocks that have temporary effects, right? So that in the practical setting, if, for example, we think about productivity shocks, that if some technological breakthrough was improving productivity, hopefully that's permanent. Right? Hopefully we will not forget about that technological breakthrough again and at some point fall back to earlier modes of production that are less productive. But at the same time, we'll probably have some shocks, maybe, for example, those demand policy, that at least in terms of output will only have temporary effects, not long-lasting ones. And so the VR, when it has used roots, we'll call it the so-called vector error correction model. We'll talk about the terminology as we get there. Such a VR model can have both shocks that have permanent effects and other shocks that do not have permanent effects, that only have temporary effects. And the second thing that we're going to learn about these VRs in the context of unit roots is they'll actually give us, even though the model per se, when we started discussing VRs, right, we stressed the only economics is the set of variables that we bring in. Otherwise, we don't bring in economic theory. We'll see we also get within these vector correction models a natural decomposition between long-run relationships and the short-run dynamics, and gets, in that sense, structural information about the economy, about the underlying set of variables into the model without per se resorting to economic theory. And I think that will be a second nice aspect to see, and so brings us yet a bit closer, right, towards the fully theory-oriented, focused DSGE models that we'll look at in the last block. Okay, so back to a VR1 model, nothing novel here, right? This is again a first order VR with the IID shock, so the zero mean vector, constant but non-diagonal variance covariance matrix. And if we want to learn about how in such a model YT is affected by current and past shocks, right, we resort to what we had done earlier, rewrite it as a function of initialization, here in period 0, plus shocks from period 1 to all the way to the current period T. Right, and then use the diagonalization of the matrix A, once again, to realize this is going to be driven, this effect of past shocks, by how this matrix of eigenvalues of A, lambda, behaves as J tends to infinity. Very much question number 1 on the problem set, right? Always applicable, and indeed, as we recall in the morning, what were the eigenvalues of that coefficient matrix A in the first question? 1 was 1, right? And so this matrix lambda did not tend to 0 as J tends to infinity. Well, here I have another example where that is true. The coefficient matrix A, where one of the eigenvalues is 1 and the other one 0.7. We calculate the corresponding eigenvectors. This decomposition, of course, satisfies diagonalization, that if I pre-multiply A by V inverse, post-multiplied by V, I get this diagonal matrix with the two eigenvalues along the main diagonal, and know, of course, again, completely in analogy to what we did in the context of question 1 of the problem set, that this coefficient matrix does not converge to a 0 matrix, but to a matrix that in this case has the one on the lower right-hand corner. The only difference to the morning, where I guess it was in the upper left-hand corner that is now in the lower right-hand corner. Now, what I also did in the morning, right, in the context of the MATLAB commands, is I showed you where does that term in v times lambda to the power of j times v inverse tend to as j tends to infinity, and we have a non-zero matrix. Now, how in general, if you don't just want to do numerically, but want to show algebraically that indeed you're going to end up with permanent effects of shocks, how can you rewrite the y process as a function of current and lag shocks so that it decomposes into that part that is driven by permanent effects of shocks and that part that is driven by temporary effects of shocks? In this case, of course, the one that's associated with the eigenvalence, that's 0.75, is what gives us the temporary effects of shocks only. And the one that's associated with the eigenvalue 1 is the one part that gives us the shock that has permanent effects. Without derivation and without expectation for you to derive this, let me just write down what turns out to be a general moving average representation that is yt as a function of initialization and current and lag shocks if some of the eigenvalues of the VR are equal to unity. And the problem in terms of getting the moving average representation in this case is, think of having a VR I minus ALYT is equal to UT. I suppose in the extreme case that all eigenvalues of A were equal to unity. All eigenvalues of A are equal to unity. What is the matrix A? The identity matrix. Right, the identity matrix is 1, 1, 1 along the main diagonal. 0 is ever on the off diagonal. This clearly must have all eigenvalues equal to 1. It's already diagonal. Right? You don't need to diagonalize it. Now suppose this was true. A was equal to I. Could I invert this in simple terms? Think back to the univariate case. This would be 1 minus L. Is 1 over 1 minus L well defined? No. I would need a conditional here that's an absolute value less than 1. This would be well defined if I have a row on it, and that row is an absolute value less than 1. Then this is 1 plus row plus row squared plus root to the power 3. This converges. But if this row was equal to 1 in the univariate context, this is not a converging geometric sum. In the matrix context, this is not well defined. And so you have to put in some special effort to invert that polynomial. Again, without derivation, I'll not go through all of the derivations. 54 gives you the result. How you actually can rewrite y in moving average representation if you have something. There's a lot of notation in there. So the first thing to notice, please, what is the coefficient here on those shocks that we are just adding up from period 1 to the current period t? A constant matrix that doesn't depend right on how far ago the shock happened. But secondly, what is that matrix? V times the limit as j tends to infinity. Matrix of eigenvalues on the main diagonal, lambda to the power of j times V inverse. We just call this henceforth the matrix C. The that's just a limiting expression. What does that matrix A in the limit tend to as we take the higher order parts? Right, that's the part here. Given that these shocks, whether they happen in period 1 or 2 or 3 or the current period, what is always the impact on YT? The constant matrix C. It's not as simple as in the univariate context, where the effect of a past shock on the current Y, when we had permanent effect, was always 1. It's constant. Right? It doesn't depend on how far ago that shock happened. And that means it has permanent effects, this component, because irrespective of when the shock happened, the impact on the current period Y is always the same. Whether this is a current shock, a recent shock, or long ago shock, the impact matrix now is C, but please do note that C is exact that limiting expression. Right? How does Y depend on a shock as we saw with first impact? But that limiting expression is now impact of the shock at any point in the past. And this is what would be in the scalar context. The C would be just a 1, and telling us any past shock affects the current Y with unit coefficient. Now it affects it with the impact matrix C. The second part, C star of L, is A to the power of J minus the C matrix. Right? This is exactly the C matrix here that we subtract from A to the power of J in defining the coefficient matrix or the coefficient matrices on the second polynomial. Heuristically, we take out from A to the power of J the permanent effect. And if we take out from A to the power of J the permanent effect, what should be left? The temporary effect. Right, so this is going to be the temporary effect. You can actually also formally show that C to the power of J, I've written it down for my specific numerical example, right, that I was giving on the previous page. The A matrix in 48. We've already written down what is the limit as lambda j tends, as j tends to infinity of lambda to the power of j. We've also written down here what is going to be the limit of z j star, that matrix in the second polynomial as j tends to infinity, irrespective of v, right? Because this thing tends to 0, this is clearly 0. Right? Of course, this is not a proof that this is always going to be just the temporary effects, but it is. It is actually true. Right? It intuitively, again, because we take out from A to the power of J the permanent effect. What should be left after taking out the permanent effect? Just the temporary effect. And again, you see in the specific example, Cj star clearly tends to 0 as J tends to 0. Right? So this is actually the decomposition of the process when we have some eigenvalues that are equal to 1 into what is the part that reflect shocks having permanent effects, the part that's associated with the eigenvalues that are equal to 1, and the second part is the one that only has temporary effects associated with those eigenvalues, 0.75, that are less than 1. Also nice to see for this example again. I just like an example in the context of question 1 on the problem set on VR models. The C matrix is such that that shock that's associated with the eigenvalue that is equal to 1 affects both elements of YT. Because both elements are at 1 because they're both subject to a permanent shock affecting them. Right, it would have to be that one row is just in zeros, then one of the variables wouldn't be affected by the permanent shock, but these rows are not 0. I mean, this is a deficient rank matrix. If you notice that's fine, but that doesn't change the fact that one shock that's associated with the eigenvalue that's equal to 1 affects both elements of T, right? Because these rows are both non-zero. And of course, if we multiply this out, right? If we multiply this out, the temporary shock is also going to affect both brackets. So this is going to be a matrix if you multiply it out that's also not zero in any of the rows. So the temporary shock associated with the eigenvalue 0.75 also affects both brackets. But that doesn't change the order of integration. The only thing that affects the order of integration, of course, is the shock that has permanent effects, and that renders both variables in our example I1. You could generalize this to more than a bivariate VR, and the core points from this bivariate VR in our example would stand. In general, as soon as you have some eigenvalues in the VR that are equal to 1, the permanent impact of the initialization is there, stays around, and is not going to ever be lost. The initialization matters forever, just like in an AR or an AMA model. If we added a unit root, initialization matters forever. The rank of the matrix C, this matrix that pre-multiplies those shocks that have permanent effects, here is 1, because we have one eigenvalue that is equal to 1. But in general, the rank of this matrix C would be equal to the number of eigenvalues of the quotient matrix in the VR that are equal to 1. The number of eigenvalues that are equal to 1 drives the number of shocks that have permanent effects. And that's reflected in the rank of the matrix C. Right, again, here you see she's still rank deficient. Same first row and second row, obviously, this matrix C only has rank 1, not rank 2. It's rank deficient. One shock that has permanent effects in a higher dimensional setting, again, the number of eigenvalues that is equal to 1 is going to be equal to the rank of this matrix C, and therefore it's going to be the number of shocks, linearly independent shocks, that have permanent effects. And finally, for this component with the shocks that have temporary effects, that part, of course, involves those shocks that in the limit, as J tends to infinity, the impact of these shocks is 0, because all brackets. Now, why are these models called vector error correction? Right? I mean, if you look at that representation 54, you might say, I don't see any error correction in these models. I just see some shocks having permanent effects, I see some shocks having temporary effects, but where's that label error correction coming from? That comes from yet another rewrite of this VR. And this time a very simple one that we can algebraically readily understand. What happens if I'm in the case of a VR1 and I subtract from both sides of my VR1 yt minus 1. The transformation that we did for Dickey-Fuller, right? Dickey-Fuller was just univariate, now it's in the system. But if you want to remember how to get to the error correction, it's kind of applying the same transformation as Dickey-Fuller did to the univariate AR1. All right, so on the left-hand side, I have the first difference, delta yt. On the right-hand side, I have the matrix A, yt minus 1, minus the identity matrix times yt minus 1. This matrix will get a special name too. We'll call it the matrix pi. A minus the identity matrix, we'll call it pi. We'll calculate pi in a second to see what is its special nature. And all that's left is ut. Right? It just was subtracting yt minus 1. That's all that we did. is subtracted on the left-hand side, is subtracted on the right-hand side. Why is this called arrow correction? Well, let's take more closely a look at this matrix I. First for my numerical example. Right, if again use the matrix A that we had in 48, for which we know one eigenvalue was 1 and the other 1.75. If I simply calculate the matrix I, which is just A minus the identity matrix, look at the resultant matrix, and you clearly see I go across columns, but of course you can also go across rows. The second row is 1/2 times the first row. The second column is minus 1 times the first column. Linearly dependent rows / columns. What is the rank of the matrix pi? 1. Has to be 1. Right? It's not a zero matrix, but it's having linear dependent rows / columns. So the rank is 1. Now, once more without proof, if you have a square matrix that is of efficient rank, here a 2x2 matrix that is of rank 1, you can decompose it into the product of a 2x1 vector alpha and a 1x2 vector beta transpose. That's generally true for any rank efficient matrix. In the general case, you could say, well, how does this generalize? In the general case, I had a k by k matrix A, right? A was k by k. And suppose the rank of A is R, where R is less than k, but larger than 0. That is, it's not a zero matrix itself. I can rewrite A, or maybe I should stick to the notation here, right? So that you don't think this is my original A matrix, this is my pi matrix, of course, right? That I do the decomposition on, so maybe that helps to denote and see the pi matrix too. I can then rewrite pi as in 60 alpha times beta transpose. Remember, pi is k by k, because alpha must be then having k rows, and beta transpose k columns, otherwise you couldn't get to the dimension of pi. You can conjecture what is the number of columns of alpha and the number of rows of beta transpose. Right. That's the general decomposition that we're using in 60. And that's again a result from linear algebra. That's not impossible, but also not entirely trivial to prove something like this. And if you multiply it out, of course you do see, as in the general case I get here, the 2x2 matrix. In the general case, of course, I get a k by k matrix. Now, let's use this, the right-hand side of 60. Right? What is the product of alpha and beta transpose? To solve for alpha 1, alpha 2, beta 1, beta 2 in that specific example of the matrix in 59. If you do the algebra, just simple algebra, you'll find that alpha 1 is minus 1/2, alpha 2 is minus 1/4, and beta 2 is equal to minus beta 1, or beta 1 is minus beta 2. That is, if I normalize beta 1 is equal to 1, beta 2 is equal to minus 1. Now, what does that mean, right? If I think about beta transpose times y, it just said beta must be 1 minus 1. Right? It says that beta transpose y is y1 t minus 1 times y2 t minus 1. Why is this of interest? Well, let's look back at this representation in 38. for the specific VR, right? Where we know one eigenvalue once more of A is 1. So what are the elements of Y? They're both I1, as we said, right? We learned that from our earlier presentation in 54. We learned from specifically 56 that both elements of Y are a function of the permanent shock, so they must be both I1. Y1 and Y2 are I1. With that knowledge, what is delta Y? Y is I1, what must be delta Y?
I0.
I first difference, the process that is integrated of order 1. What is the first difference of a process that is integrated of order 1? I0, right? So the left-hand side of 58 must be I0. The UT term on the right-hand side is IID, in terms of order of integration, I0, right? That's just ID, the most extreme case of an I0 process. So this is I0, that is I0. On the left-hand side, we have an I0 term. We grade it to something on the right-hand side. If we grade, it also must be the same order of integration on the right-hand side, right? There's no way that something that is I1 could be equal to something that is I0. Then the I1 term has unbounded variance, and the I0 term has bounded variance. How can they be equal to each other? Impossible. Right? So it must be that the whole right-hand side is I0. Given that U is I0, what then must be this term in pi yt minus 1? I0. Right? There's no other way. Otherwise, this equality couldn't hold. Again, delta y is I0. U is I0. An I0 process can only be equal to another I0 process. It cannot be equal to an I1 process. And so the whole right-hand side must be I0, and given that U is I0 as well, that cannot be the trick. That made me know U would be I1, and therefore this term could be I minus 1, and then they somehow add up to I0. Can't work, right? Because this is I0. Then this term in pi yt minus 1 must be I0. Therefore, when we want to decompose pi to alpha beta transpose, and we know the alphas are just these coefficients in -1/2, minus a quarter, multiplying for the first and the second variable. This term in beta transpose y, what must be the order of integration of beta transpose y? It must be I0. Right? It must be I0 because the alpha is just applying another transformation by -1/2 by minus the quarter. Right? That's not changing the order of integration, that's just multiplied by some number. So beta transpose y must be I0. That is in our specific example. We had calculated B transpose y is y1 t minus 1 minus y2 t minus 1. That must be I0. In other words, a linear combination, just y1 minus y2, is I0, even though what again was the order of integration of y1 and y2 individually? I1. That's what we call co-integration. Allow me the following analogy, even if you think maybe it's not econometric, and I don't think it's econometric, but maybe it helps you remember these things. I think about a I1 process. A random walk with drift. Right? An I1 process with an intercept term, yt is equal to alpha plus yt minus 1 plus epsilon t IID. This is what we call a random walk with drift. They're I1. You could call these two variables that follow this framework for drift, you call them drifters. Right? They drift ever further away from the initial condition. Because we know, right, they eventually driven by the drift. So they drift ever further away from the initial condition. But when these two drifters get together, they're inseparable. Because they are zero, if they are zero, right, they must have a constant mean, they converge back to the mean. So, it's like, if you had two individuals who are like drifters. When they meet, they have a never separable relationship because they always converge back together. It's a very romantic concept in that sense of integration, right? But hopefully that, again, this is not econometric, this is not economic, right, this example. But what I'm trying to convey with you through that example is kind of stunning that it happens. Right? Kind of stunning that it happens. And that's exactly what econometricians thought for a long time. If variables are I1, they'll never have an equilibrium relationship. They're just, they're unbounded invariance both. How could they have an equilibrium relationship between them? But co-integration uncovers they do. They do because there's a linear combination between the two of them. That is I0. By definition, I0 means, right, it has a time invariant mean. It converges back, that linear combination, after every shock, it converges back to the mean. Right, and so in economics, it would mean that one process, say, is income. That is I1 because of productivity shock. Consumption, probably, if income is driven by a permanent shock in productivity, you can also imagine that consumption is going to be driven eventually by this shock in productivity. The linear combination of them, or the consumption-income ratio, right? I mean, the linear combination in logs, log consumption minus log income. Take out the log, it's the consumption-income ratio. That is still I0. And that makes good sense, right? That the consumption-income ratio doesn't drift to zero, it doesn't tend to infinity. Either one is not possible. Right? If it drops to zero, people starve. If it drops to infinity, people cannot eventually pay any consumption anymore because they have been vastly overborrowing if they have infinitely many more amounts of consumption expenditure than is the number of things. Right? So the consumption-income ratio, that better be bounded. That forms the equilibrium relationship, consumption and output, even though both variables may be I1. And that's the economic context, right? In which we are going to use this more generally. A vector is said to be co-integrated if each of the elements of yt individually is, say, integrated of order d, whereas the linear combination of the elements, beta transpose y, is integrated of order d minus 1. We are only interested in the case where d is equal to 1, right? We are only interested in series that are integrated of order 1 or 0. So if they are initially integrated of order 1, they may be co-integrated. If there's a linear combination that is integrated of order 0. Then those two values are co-integrated. Right, and so from that perspective, if we now go back to this error correction relationship, we have a structural, a structural decomposition, right, of y. We have that co-integrating relationship in beta transpose times y. And the alphas tell us what? How does y change if I'm not in the co-integrating relationship? Right? Last, of course, y changes if I have a shock. Right? The shock will always change the values of my variables. That's not the great insight of the error correction model, but the insight is, even if I had no shock, ut was the zero vector. Delta y need not be zero. It could change because initially you were not in the co-integrating relationship, and then you adjust because you're outside the co-integrating relationship, you adjust back towards the co-integrating relationship. Let me just give you a numeric example. Then can I just do the example first and then get to your question? Just to keep the line of thought, and then I really come back to your question. Let's suppose, right, we take our numerical example, where we said what is the co-integrating relationship? 1 on y1 minus 1 on y2. Right, so we said y1 minus y2 must be I0. So if this co-integrating relationship was to hold deterministically, y1 minus y2 is 0, y1 is equal to y2. Now let's suppose initially we were not in the co-integrating relationship. Just to give you an arbitrary example, I suppose initially y1 was equal to 2 times y2. So of course, relative to the co-integrating relationship, y1 is too large. What must happen according to our process to y1 and y2? Remember that we have alpha 1 is equal to 1/2, alpha 2 is equal to minus a quarter. So what is happening in this numerical example? Delta y1 is the minus alpha 1 minus 1/2 times y1t minus 1 minus minus, right? Minus 0.5 times the co-integrating vector of minus 1 is plus 0.5 times y2t minus 1 plus d1t. And what do I have overall for the change in delta y1? Right, remember I started out from y1 is equal to 2y2, or in other words, y2 is 1/2 times y1. If y2 is 1/2 times y1, for this that expression minus 0.5 times y1 plus 1/2 times y2. If y2 is 1/2 times y1, this is minus 1/4 times y1 plus the shock for the second variable. Right, remember again, alpha 2 is minus a quarter. Minus a quarter times 1 on y1 is minus a quarter. Minus a quarter times minus 1 is plus a quarter times y2. Remember again, y2 is 1/2 times y1 initially. And so this is minus 1/8 times y1. T minus 1 plus t1t. Which one shrinks faster? y1. And why does y1 shrink faster? Because it's too big relative to the co-integrating relationship. Right? And so the model drives us endogenously back to the co-integrating relationship. And that's why it's called error correction. Errors, in a sense, you're outside the co-integrating relation. And if that happens, that you are outside the co-integrating relation, the model structure drives you endogenously back to the co-integrating relationship. And that's why it's called error correction. And again, it's a very nice structural decomposition in that it distinguishes between what happens in the long run. If, of course, only if there is such a co-integrating relationship in the long run, among I1 variables we have an I0, that the stationary relationship that's always going to head back to its mean. Overall, the process is I1 and adjusted over time because A, shocks, it always does that, any process adjusts because of shocks, but B, the novel thing is, if you're not in the co-integrating relationship, then the alphas drive you back to it. And that's error correction. That's the story. So now any questions?
The latest thing is this case, beta is 1 and minus 1, so it is so very special, but like you said, like beta can be other things.
Of course, yeah. I mean, you generally want to normalize in that conic weighting relationship. You will normalize one element, and maybe the most common normalization is if the coefficient on beta 1 is non-zero, normalize that to 1. But the beta 2 need not be minus 1. That's just this specific numerical example. It could be minus a half, it could be plus 3/4. That's dependent on what is the, in our Biret example, first order example, what is the coefficient matrix A? Right? And so you'll estimate, of course, that coefficient matrix A in a practical setting. If it had at least one eigenvalue that is equal to 1, then all variables are at 1. We might have a conic weighting relationship. And to figure that out, you calculate the matrix pi in 58, right? Check its rank, and the rank of this matrix pi is equal to the number of conic weighting relations. And then, just like in my specific example, following the type of calculations, right, that I have in 60, 61, 62, you calculate what exactly are these elements of those conic weighting vectors. Under the normalization that you normalize one of its elements to 1, you calculate what are the other elements. This is a very simple example. I chose it, of course, actually to be exactly like that, right, to be 1 minus 1, so that we have that simplest type of conic weighting relation in deterministic terms, that y1 is equal to y2, that's why I picked it to be that thing, so I don't have another number floating around here. But in practice, unlikely that the conic weighting vector is exactly 1 minus 1. Well, maybe if you take my example of the consumption income ratio. But as I said, if we have a data on consumption, data on income, they're both I1. And then we might, as macroeconomists, be interested in what is the consumption income ratio. And there you would also expect the conic weighting vector between consumption and income. If you normalize the coefficient on consumption to be 1, the coefficient on income is a minus 1. But that's just another example where that again would be the conic weighting vector. In general, it might also be not minus 1, but minus 0.8 or minus 1/2. That's to be determined in the data. But in the specific example, right, the consumption income ratio, of course, in logs is 1 times the log of consumption minus 1 times the log of income. So then you again have an example where the conic weighting vector is 1 minus 1. But these are just examples. This is not generally true, and you'll see it in data when we estimate this for our model. These conic weighting vectors do not be 1 minus 1, but there's just one component that may be 1 because of normalization. The others are some other number.
So as long as we can find, like, as long as beta here exists, there will be a full integration relationship.
Right, and that's there, right? Whenever the matrix pi is not a full rank, so that you have this decomposition of pi into alpha beta transpose. Of course, if pi was the zero matrix, when is pi the zero matrix? When A is the identity matrix. Then our early example here. Then you basically have, if A was the identity matrix, you have 3 value walks. If it's 3 variables or 2 value walks, then it's 2 variables. They have nothing to do with each other, right? But that shows you, even if the variables I1, it's not a guarantee that there's a conic weighting relationship, right? If it was that A was the identity matrix, it doesn't have a conic weighting relationship, right? So it's not a must that there's a conic weighting relationship with the variables I1. But if that matrix A minus I is non-zero, rank deficient, the rank of pi is the number of conic weighting relations. Right here, clearly that matrix is of rank 1. Means we have this one conic weighting relation between y1 and y2 that we established to that specific set of coefficients.
So actually, like the beta, when we multiply with the other past values, that is like the long run relationship between
Right,
those
exactly.
that
It's the strength of the long-run relationship, right? If it was in our example here, not 1, but say in a sum coefficient beta 2, beta 2 would measure if y2 changes by unity, what is the resultant change that we will have in y. Right, so it measures that indeed the strength of that long-run relationship.
So we have to, like, even though we know that the y2 is I1, we still will apply the VAR models, and then we check for the integration, co-integration.
Exactly. And that's what we'll do in Stata. When we revisit our variables with our funds rate, the rate of inflation, I'll then switch to the level of output. That's exactly what we'll do. First, do unit root tests, right, to check that those variables are I1, that they can be together in a VR, where all variables are I1, and then we check on the integration.
It's also surprising because, like, in the evaluate, you only care about the stationarity, so we will different it right away. In this case, if we're trying to look for the stationary variable first, we cannot find the long-run relationship.
That would be correct. Now, we'll talk about that in practice a bit too. You know, again, these unit root tests, there's of course always some degree of uncertainty associated with them too. So if it's borderline, we might still say I could give it a chance to put everything into a VR where every variable is I1 and then do the co-integration test nonetheless. Right? There's no certainty in practice as a variable I1 or I0. So sometimes we may be in a gray area, we may not be entirely convinced that every variable is I1, but we may still give this co-integration test, which is at the end of the day, right, a test on the rank of this matrix pi. We may give it a shot. Any other question on that derivation? Right? So to be very clear, I'm not going to ask at any point in time to derive 54 with all those elements in 55. That's way beyond the scope of this course. This was just to show you I'm not arguing on the basis of specific numerical examples. That there is a general logic and also general algebra behind what I have argued in the specific bivariate example. That's why I wanted to have this expression in the slides, but you're not expected, for our VRs to come up with that. What might be asked of you is, right, that just like in this example here, again you find out the number of eigenvalues. If one of them is 1, then you say, aha, okay, then let me check what is that matrix, right, with which those shocks affect in the long run the elements of Y. You can readily compute that, right? Well, in the project you can readily compute it because you can even use software, right, to plug in for the inverse and so on, so you can readily compute that with the help of software at least. Now the context makes it a little bit more algebraic work. You can figure out, yes, are all these variables permanently affected by that shock? That's associated with the eigenvalue 1. You should expect that that's going to happen. So all elements of Y in theory are I1. And then you go for the check on co-integration using that correction relationship check on the rank of the matrix I, and can, just like we did here, decompose it right into the co-integrating vectors, measuring the strengths of the long-run relationship between the variables, and also having calculated the alphas, convince yourself and anyone else that the model has error correction. That is, if we have any relation between the y's that is not conforming to the co-integrating relationship holding deterministically, we'll have changes in the y's that bring you back closer to the co-integrating relationship. That's the main thing that we have learned. On this slide, again, I state this for general K variables. We are, as I said in the context of this example, if the range of pi is 0, We basically have just a bunch of random walks that ended up in one model together. That's not going to very often happen in economic analysis, right? Because that basically means the variables don't interact fully, except perhaps with the L terms. Interesting case is when the rank of pi is larger than 0 but less than full rank. Then we have R co-integrating relations, and if for some reason the rank of pi was full, what's the only possibility? If the rank of pi was full, but we have the notation in pi. Here in 38. If the rank of pi was full, remember again our earlier reasoning, what must be delta y? I0. Right? Because if y is I1, delta y is I0. If y itself is I0, except for that case where the long run variance was 0 as well, it's I0 too. Right? So generally when we first difference in I0 process, it's I0. Again, that's just that specific example that we had last week when we took white noise I0 process first difference it. Actually the long run variance was 0 and not finally positive. But in general, if a process is I0, most of the time the first difference is I0 as well. So irrespective of whether y is I1 I0, delta y should be I0. Now if delta y is always I0, u is I0, and pi is a full rank, then you cannot do the decomposition like you did before. What has to be y? It has to be I0 as well, right? Because in essence it says any linear combination of the y's is still I0. And then y must be I0. And that's what is written down in slide 34 as case 2. If, remember we have k variables, if the rank of pi is k, that is a full rank, all variables must be I0. Okay. So on slide 35, just on a side note, I don't think we need to spend much time on it, but maybe I should say a minute something about it before you later again think about this endlessly and think something must have been wrong in what I said today. You might, upon some thinking, realize this decomposition that I gave you in the case where pi is rank deficient into alpha times beta transpose, pi k by k, rank R, so alpha k by R, beta transpose R by k. This is not unique, and that's true. Right? Because you can always sandwich in between alpha and beta transpose Q inverse times Q, because that's by definition the identity matrix for any non-singular matrix Q. Right, and so of course the decomposition is not unique in the sense that it doesn't give you a unique beta, but Q beta transpose can just as well be a co-integrating relationship as beta itself. And alpha Q inverse can as well be the adjustment of the y's to the co-integrating relationship as alpha itself. The only way how you could make this unique, alpha and beta, is how? If you restrict the Q, if you put enough restrictions on Q so that you knew the value of Q. Think about it, Q is R by R. The only restriction is that it's non-singular. So it's R squared parameters. If I have R's equal to 1 co-integrating relation, how many restrictions do I need on Q? 1. R by R, 1 by 1 co-integrating restriction. And that's what was it? Normalization, right? If we normalize this first element of beta 1 to be equal to 1, that's my one restriction. I have imposed one restriction. So in the case where I have one co-integrating relationship, we are fine. But if we had 2, say, I suppose R was equal to 2. To pin down Q, you need R squared, 2 squared, 4 restrictions. Now when R is equal to 2, you have 2 normalizations, right? You have 2 co-integrating vectors. You normalize the first, you normalize the second, you have 2 out of 4 restrictions. But where are the other 2 coming from? Maybe in a specific context, we have some economic theory, right, that restricts the co-integrating vectors. And that may make them unique together. But that's a very context-specific story. We can't tell that here in our general analysis. So in general, the co-integrating vectors are not unique. That's what we have seen in 70. When Stata gives you specific co-integrating vectors, and we have more than one co-integrating relation, it will somehow search for other restrictions. And what does Stata actually do? It restricts also the length of the eigenvectors. And that has nothing to do with economics. That's a purely mathematical restriction. So if you want, in the case of more than one co-integrating relation, a very sensible, plausible interpretation of betas, you have to restrict them somehow from economic theory. But it's not the main thing for us, right, because we want to forecast. We are not, within this course, specifically interested in interpreting the betas. So from that perspective, we can just live with the fact if that decomposition is non-unique, because we care about the question, does incorporating the co-integrating relationship, does that help us to forecast better? That's going to be our question. And then you're not that worried about it, but if you want to use this analysis in a different context, right, where it's not, in quotes, only about forecasting, but you wanted to interpret these long-run relationships, what is the strength of that long-run relationship? Then, of course, you need for beta to be unique, right? And then you have to think about coming through with such restrictions. So just to clarify that, and not that you later write a paper and say, but I said, just take those data estimates or something like that. There you have to be a bit careful. All right, next couple of slides. Extend this to the case of a higher order VR, not a first order VR, but a peak order VAR in 71. How does the co-integrating relationship then look like? Think about our earlier hint. The transformation from the VR levels to the co-integrating relationship is like the Dickey-Fuller transformation. For a higher order AR, how did the augmented Dickey-Fuller regression look like? The first difference on the lagged level, lagged once, and additionally, lagged first differences, first, second, all the way to P minus first lagged first difference. Now this is because not the Dickey-Fuller regression, this is a systems equation model, but the intuition is exactly the same. You can rewrite this VAR in levels when it's more than first order, still as delta yt as a function of yt minus 1, with the coefficient matrix in yt minus 1 that's still that I matrix, the rank of which determines the number of co-integrating relationships, just like in the first order case. But in order to get ut to be ID, you need to add on lagged first difference. Same intuition as in the Dickey-Fuller context, to get all the dynamics in. If in levels you have a higher order model, you need in the correct interpretation these lag first differences. And that's all. Right? The rest is again just like in the first order case, because now we care about the matrix pi, and it's about inspecting the rank of pi, and the rank of pi is the number of co-integrations. That's just a little bit extra around this core co-integration model that we had in the first order case relative, right? If you look back to that error correction station for the first order VR in 64. Relative to 64, what do I have in the case of a peak order VR? I have these additional lag first differences, delta yt minus. That's the only substantive change. Right? Okay, so that covers higher order VRs. Otherwise, fortunately, conceptually, there's nothing new to say about those. And then this co-integration rank test, that's on slide 38. I'll discuss it in state. Basically, what Stata will do for us is a test for the rank of pi, right? That's our number of co-integrating relationships. That is based on the number of non-zero eigenvalues of pi. I'm throwing a lot of results on linear algebra today. How can you tell the rank of a matrix pi, that's a square matrix, beyond just trying to see how many rows, columns are linearly dependent? You can calculate again the eigenvalues and count the number of eigenvalues that are non-zero. The number of non-zero eigenvalues of pi is equal to the rank. So in other words, the rank deficiency is the number of zero eigenvalues. And that's basically what this test statistic, the so-called Johansen-Trace statistic in Stata will do. It estimates our matrix pi, calculates its eigenvalues, and then tests for any desired number of eigenvalues being non-zero relative to some alternative hypothesis. That's what we'll do. But again, I'll probably best explain how Stata does it once we see Stata output, and then we can go into more in a specific example. But all that you would please remember from that slide is we check on the rank of the matrix pi by estimating it and then calculating the number of non-zero eigenvalues, and that's pinning down the rank of the matrix pi. And that's underlying the so-called Johansen-Trace test that will happen in Stata. For lag order selection, we can still use Akaike and Schwartz, right? Remember also in the ER context, irrespective of whether the model was stationary or not, we said we can use our standard information criteria. Same thing here in the systems context. And also remember, if we had a Riemann model, we had on the left-hand side also the first difference. We wanted to forecast back to levels, and then said to get the level forecast, you simply add to the current level all the projected changes up to that point in time for which you want to forecast. 75 is exactly the same formula as in the slide set on the Riemann models when we talked about forecasting, where we also had that the decomposition of the level in the future time period into the level in the current time period plus changes between the current time period, t plus 1, changes in t plus 1, t plus 2, all the way to changes in t plus h minus 1 to t plus h, right? That's what this thing is. Okay, now let's go to the data. And for that, just maybe pick up in slide, in line 98 of that do file. That's where we left off before, right? Sorry. So, as we said, right, in discussing this material before, we'd like to be sure that all of our variables that go into the V are I1. Right, and so in practice, that might suggest we first do unity tests for each and every variable that goes into the VR, so that it is really I1. Because it has to be, right, according to the structure of our VR model. Remember, there's at least one eigenvalue in the relevant coefficient matrix. That's why our model we call A star in that first order representation of the higher order VR. If at least one eigenvalue of that matrix was 1, then it should be that all elements of Y are eigenvalue. Right? And so before we put them into VR, they should all be eigenvalue. So in the do file, you have first the root test on the federal funds rate, then on the rate of inflation. And then for output, I switch from the output gap back to output. Why? Because per se the output gap, right, is the difference between potential output and actual output. And they are likely to have the same permanent shock in there. Right? Anything that shocks productivity forever will change potential output, just the same as actual output. So there should be little hope that the output gap is I1. So that's why I switch back to actual output. In this VR now that we want to partly have in I1 versus VR. Let me suggest I skip here the root test on federal funds rate and rate of inflation. The root test on the federal funds rate we had anyway done before, right? When we looked at the AMA versus ARIMA models, and for inflation, the command syntax is of course one-to-one the same as it was for the federal funds rate. Just have a look. I just want to do the one for output for the reason that one of those questions that I got over the weekend said, let's see an example where the series has a trend. Right, and so let's look at the plot of the output series within our sample, and non-surprisingly, output is upward trend. So I could now formally estimate a model, right, where I said I add to a unit representation of output, say in the form of an ARIMA model, I added specifically a drift and estimated that drift. Or I add to an AMA model for output a time trend and estimate that coefficient on the time trend, and either way check is that coefficient significantly non-zero. Why do people rarely ever do it? Because it seems so clear-cut, even to the eye match. Right? If you're not so clear-cut, yes, maybe run a separate regression of your variable on the time trend, and if that coefficient on the time trend is significant, statistically significant, you found evidence that it's trend stationary, and if that coefficient on the time trend was insignificant, you would reject that now that the series is trend stationary, we would probably back to it having a low time trend. Okay, so here I clearly want to add a time trend in output. So I need to modify my command syntax a bit. Right? So that's what I'd like to show you here. First of all, I course do a lag order selection on output. You can also, even if it's univariate, use VAR SOC. But that works in the univariate context just as well, because you could also go back to this ARIMA SOC that we had earlier on. You select the lag order. And so let me just execute that. When you do that, you find both according to Akaike and Schwartz one lag. That seems enough. To account for it, so of course in terms of the Dickey-Fuller test, that's the default Dickey-Fuller test, we don't need an augmentation. Right, and so in the next line in the do file, it says the augmentation is 0. You don't need to add lag first differences to that default Dickey-Fuller regression. And in terms of the specification of the deterministic model component, we now add the option drift to Dickey-Fuller. If you look back earlier for the federal funds rate, well, it's up there, right? For the federal funds rate, we didn't say anything about long deterministics. Then Stata presumes there is no linear deterministic trend in the series. Here we add the drift. You need to add it explicitly, right? So that Stata does consider the whole setup under the specification where there's a drift/linear deterministic trend. That's the difference relative to what we had before under the federal funds rate or the rate of inflation. The rule test. So do that, execute that Dickey Fuller with that drift option added in, and it gives you a probability of 5.6% rounded. So both at the 1 and the 5% significance level, output has a limit. The evidence is that output does have a limit. Good. For the Dickey Fuller GLS test, I mainly want to do it to also can illustrate how to account for the trend. Right before we said no trend, and now we just dropped the no trend. That's the specification of the DFGLS test. Tools execute do. It wants us to look at the model according to the modified Akaike criterion with one leg. And at one leg, we have rather strong evidence that there's a unit out. This time, actually, the last test is much stronger preference to a unit root than the augmented Dickey Fuller. So that can happen too. It need not always be that the augmented Dickey Fuller is quite sure. Yeah, there's the unit root, and the Dickey Fuller GLS is not so sure. Because it's just the other way around. Right? Where here, of course, according to the Dickey Fuller also at the 1 and 5%, but we haven't. So pretty strong evidence claim of unit root. We know already for the federal funds rate it was a bit more marginal. I'll leave you to let you engage in the unit root testing for the rate of inflation, but I'll forge ahead anyway now, right? And that again goes back to the earlier question. Even if I'm not 100% sure, what should I do? Well, if you think it's a sensible possibility that all the series I want, I can go ahead with my current equation rank test. And that's the VEC rank test. VEC rank will estimate now our preferred order VAR and check for the rank of the matrix phi. That is check for the number of current equating relations per this Johansson trace statistic. That's the test that will now reinstate. So let's execute the command so that we can look at the output in detail and go through it carefully to see what is suggested here for the number of quoted-grading relations. So you get a table in Stata where you have one column, that is the trace statistic. That's what we want to look for, and corresponding to it critical values at the 5 and 1% significance levels. We don't get p-values for this in Stata, but we have the 1 and 5% critical values to inform you about whether we might or might not want to reject. So now what is the now? You go through it row by row. You always start in the first row. In the first row, what is the null hypothesis? That the rank of the matrix pi is 0. That is that we have 0 current equating relations if all variables were I1. Each and every variable is an I1 model on its own without forming any current equating relationship with any of the other variables in the model. Right? This is like our example before, that you just put 3 random blocks into a VR. They're all I1, but they have nothing to do with each other. And you don't find a current equating relation. So that's the first now that we check. We get the test statistic, can compare it to the critical values, and find that the test statistic is less than the critical value at 1%, but well larger than at 5%. So at 5% significance levels, we reject the null of 0 co-integrating relations. Suppose I go with that, right? Of course, I cannot prevent you from saying I go with the 1% significance level, and therefore take away from this that there are no co-integrating relations. Well, if that's what you feel, keep using the VRs. Right? And there's no error correction representation that is useful to exploit because there's no co-integrating relation, so we just stick to that VR index. But if I go with a 5% significance level, I next turn to the row rank is equal to 1. Go step by step in that table. I get a test statistic of 11.83 and see that is insignificant also at the 5% level. In other words, also at the 5% significance level, I cannot reject the null that we have one co-integrating relation. And that's all. Right? Because I couldn't reject the null anymore, I don't move to rank 2 or 3. You're done, you cannot reject the null, you stop. If that had happened in the first row, that maybe it says this is also suggesting that we are not being able to reject the null of a rank of 0, you stop there. So if you want to work with a 1% significance level, you have to stop there. Right? Then that's it. That's it. Whatever the significance level you want to work with, if the null is not rejected, you stop in that. If I work with a 5% significance level, therefore I stop in the row where the rank is 1. And that's what I do. Right, so I say I take away from this, there's one co-integrating relation. And now I estimate the vector correction model under that restriction. That there is one co-integrating relation. By the way, just notice this still says a VR3. Like we had earlier said, when we ran this should be a second order VAR. Right? So let me just change all of this to second order. And I hope this is not, if I do the rank command one more time for the second order VR, this is not going to take away the co-integrating relation. You never know. Let's just run it once more for the second order. Yeah, but no, actually it is going a bit in a different direction, right? It says, now for sure I reject at both the 1 and 5% significance level 0 co-integrating relations. At the 5% significance level, I still reject one co-integrating relation, but not at the 1% significance level. And if I operated at the 5% significance level, I would want to have 2 co-integrating relations. Well, if I take that at face value, right, I should now also change, of course, in the estimation of the correction mark in line 132. I should now change the rank to 2. Because at the 5% significance level, just found evidence for 2 co-integrating relations. And make it wonderful because that way I can illustrate we have estimates of 2 co-integrating relations. They're arbitrarily identified, right? Just like in that discussed in that slide 35. Stater will put some arbitrary restrictions on the Q matrix. You can't interpret structurally the long run relationships. So helps me to illustrate that too, so I happily take that. So let's estimate this vector correction model, right? With, again, 2 co-integrating relationships, second order model, right, as we had decided upon before. Trend in brackets constant means to include a trend, but in such a form that when you rewrite the model in levels, this is still a linear trend, not a quadratic trend. A number of options for that in state. I think this is the most common option where you say, I have a variable that has a trend, right? Output had a trend, so I want to have my models in levels have a trend, but it's a linear trend, not a quadratic trend. And I have no trend in the co-integrating relation. That's why it says constant. But in the co-integrating relation, I have no time trend. Okay, otherwise it's our 3 variables again, the direct command on it reset. Right, so the rest of the command syntax is probably pretty expected. Now, if we go back into data, we get a lot of output, right? So we get first some summary statistics on this overall VER/vector correction model. We get the coefficient estimates for each equation. First difference on the first leg in level, CE1 means co-integrating equation or relation 1, CE2 co-integrating relation 2. So these are like the alphas in our notation, right? The speeds of adjustment. Then you have these lagged first differences. Just one lag first difference because we had a second order model, right? You get that across all equations. And at the bottom, you get your co-integrating relations, not economically interpretable, right? Because we have two co-integrating relations, and so the skew matrix is 2 by 2. It needs 4 restrictions. We get just 2 restrictions to normalization. Stata brings it down to the length of the eigenvectors that are associated with those eigenvalues that are 1 and that cause such co-integrating relations to be present. No economic interpretation. But for us, that's fine because we're in the forecast, right? We per se don't want to ask what is the strength of the long-run relationship between any of those three variables in our model. So for us, that's fine. We'll just leave it as is because we turn right to forecasting. So if we turn to forecasting, how to forecast for vector correction model, one step ahead, really similar as for VR, except now we need to use the option level. Right? Because the model is on the left-hand side in first differences. So if you didn't put in the levels option, Stata would forecast for you the first difference of the fellow function because you get completely different forecast than what we had before. So just like for the Riemann model, we need the level option, because tells Stata which equation from. And for the multi-step ahead forecast, maybe we call from the morning FCAS compute. I create this prefix F4. F4 on R will create a new variable F4R that I'm going to call RF4 in line 138. Those are the multi-step ahead forecast, as we said in the morning. 13 out of sample quarters, 22, 3, 4 plus the first quarter in 25. 13 quarters overall. And the rest is again very similar to what we had before. Just for the residuals after VEC, this predict residuals command doesn't work. So you please would generate the residuals yourself. That's what I do in line 148, right? I generate the residual myself. Difference between the actual value of the fellow funds rate R and the one step ahead forecast R3, and then I need to square that, and I have the root mean. Not yet the root mean, so I get the squared error, and later I will transform that to the root mean square. Right, so of course you could do that always. It's just that usually we have predict residuals, why not use it? But it doesn't work here, predict residuals for the VEC estimation, so we need to create it ourselves. But that's a small thing, right? To create the difference between the realization and the forecast, and then square that to have the squared forecast error. But again, later we'll convert into a root mean square error. Okay, so let's create that. And we'll get the one and multi-step ahead forecast. Same data as before, just looks a bit different because we have now again a wider scale overall. One step ahead forecasts. Pretty much all of them underpredict. That's perhaps a bit noticeable. Right? Usually we'd have more of a zigzag pattern of the one step ahead forecast relative to the actual ones here. Just about everything underpredicts except for the very beginning and the very end of the outer sample period. In terms of the multi-step ahead forecast, did it help us to work with co-integrating relations? Unfortunately not. Not for this out of sample scenario, right, where we have this mean reversion. And vector correction models are not about mean reversion. They're about the permanent effects of shocks combined with long-run relationships. And this is very clearly driven very strongly by those permanent effects of shocks. Right? That's the dominant component of this forecast. I can't promise that we'll see in the course another example where the co-integrating relations help crucially, but I can guarantee you that sooner or later, if you keep working on macrofinance data, you will find situations where the forecasts that impose the co-integrating relationships are a big plus. It's specific on what happens in the outer sample period, right? In this outer sample period, the main driving force is that push of the federal funds rate back to the in-sample mean, and that's not what co-integration macroequation model does want to deliver. It has these co-integrating relations. I said, oh, much better than the Riemann model. If you remember the Riemann model, I think was like this. Right? So compared to the Riemann model, it's an improvement that we have these co-integrating relations. But still, the dominant force overall for this multi-step forecast is the permanent effects of the shocks. And that's not our outer sample period. If our outer sample period was enough, that we forecasted shortly after the end shortly after the beginning of the global financial crisis, where the federal funds rate was down to the zero low bound, this would give us great forecasts. But that's not our outer sample. Right? So don't dismiss it, but of course it cannot be expected, right, that if in the outer sample period you have very strong mean reversion, that these models where permanent effects of shocks are the ones to go for. I still want to cover them, right, because you want to be covered. And when that's your out of sample growth. All right, finally, I calculate all of the other forecasts that we had before from the AR model, the ARMA model, the Riemann model, and put everything into one graph for the one step ahead forecasts. It takes a little while because it needs to select the leg orders for everything. So it's running through that, so we'll get a picture of all the different models that we had so far for the one-step ahead forecast and for the multi-step ahead forecast. Here the one-step ahead forecast. We'll do a comparison through the root mean squared error. That's faster than looking at all these plots, because look at the plots, there's nice good information. We compare the root mean squared errors. Of course, the direction model is not going to come out on top all of a sudden, right? Can't be expected, even one step ahead. And so at this point, still one step ahead. The best forecasts come from the VDAR without the error correction mechanism imposed. For the multi-step ahead too, right, we should expect that the VR will be a winner out of sample from what we had seen before, and it clearly is, right, doing better than our univariate models and doing better than models with permanent effects of shocks. But again, here you see, right, we do much better with a vector correction model than we do, because there's a mixture of co-integrating relationships and permanent effects of shocks. That's it. No RBC models today, but then we'll start that on Thursday morning, given that I'm also in the last thesis seminar for 8 hours tomorrow, and given that I only heard a couple of days ago that we didn't do RBC models, I'll do that on the whiteboard on Thursday morning. The slides that you already have on DSGE models, and I will add yet more to those before Thursday, go already into the model with frictions. That is sticky prices, sticky wages, imperfect competition, intermediate goods production sector, and so on. But on the whiteboard and in Danair, on Thursday we'll start first off in the RBC model to hopefully get a bit more intuition. Where do these models come in relative to what undergraduate math and other models would talk about? So Last thing for today, again, you can do all remaining problems on the problem set on VR models. That will be our first piece of work on Thursday. And the other thing I'd like you to do is to download the Dynea, right? Please remember from the course syllabus that you can download the Dynea from the Dynea website free of charge. And that website is under dynea.org. The manual is under dynea.org/manual, but the software itself, just go to the main site, dynea.org, and please also download the Dynea software from there. It's going to guide you through that, and it's only going to work if you have MATLAB installed. But I take Dr. Ha send you around the link of how to obtain MATLAB for this course as well. So if you want to follow things that I do on Thursday, you will need to have Dynea installed as well. And then we can take off from that on Thursday. But that may take, not ages, not hours, but some minutes it may take. So if you want to do things live on Thursday, please download Dynea prior to class on Thursday, and then we'll take it from there in terms of using that. See you maybe tomorrow for some of the master seminar sessions, but in any case on Thursday.